welcome on board. This is the Line B Engineering Process, a channel where we give a walk through on process engineering operations and design. Let's dive in. Engineers in the rough, you have a design mission on hand. Your mission, should you choose to accept it, relate the separation of air into two major components, nitrogen and oxygen, using cryogenic distillation. Feed composition includes nitrogen at 78.1% mole fraction, oxygen 20.9%, argon 1%. For feed conditions, we have 1 bar, which is equivalent to 1 ATM, and then 25 Celsius and a flow rate of 1,000 kilogram mole per hour. For the process setup, we're expected to carry out three-stage compression and intercooling and have a vapor fraction equal to or less than 0.45 before entering the distillation column. The target for our separation is a return of greater than 95% mole fraction of nitrogen and for the top of the column, and the bottom of the column we're expected to have greater than 95% oxygen return. So with this, we have the basic information that we need to carry out the simulation, but then there are little loopholes if you look deep into it. Things like our food package, our our after our three-stage compression intercooling, the temperature and pressure that we are supposed to be on before we go inside the column, things like that. But it's designed so we need to do some research to understand what particular temperature and pressure is favorable. Same applies to the food package and some other little information that we do not have. Let's set to the simulation environment. We're back to the simulation and modeling environment. And those of you who do not know how we got here, as always, we will tell you you are in the wrong dimension, rather the right dimension at the wrong time. Make sure you watch our previous content, be on the same page with us. So, today our food package of the day is not Mr. Pen Robinson. Unfortunately, Pen Robinson is not versatile in this case. Pen Robinson is suitable for hydrocarbons. Today we are not dealing with any hydrocarbon, we're dealing with nitrogen, oxygen, and argon. So PRSV right here is the food package of the day, as it is more accurate for in this type of process. So we're going to create our feed stream. We're going to call this air. Remember, for our composition, we were given a composition in our mole fraction basis, and for nitrogen we had 78.1%, which is 0.781, then 0.209, which is 20.9% for oxygen, and then 0.01, which is 1% for argon. We have successfully entered our composition, and for our conditions, we understand that we're working with 25 Celsius at 1 bar, which is equivalent to 1 ATM and 1,000 kilogram mole per hour. Right, this we have successfully created our stream, and our vapor fraction is 100% gas. It's to be expected. Now, the next thing is that we need to carry a three-stage compression and intercooling and get our vapor fraction down to a vapor fraction of 0.45 or less. Now, to do that, we understand we definitely know that we need to drop the vapor fraction, and things that drop our vapor fraction for gases is basically heating. It's basically cooling rather, and that's the reason why we have intercooling in between. Cryogenic distillation is all about carrying out separation of the mixture at very, very, very low temperatures. Now, here's the twist of the plot. We are to carry out compression and intercooling. Now, if you understand the ideal gas law, Gay-Lussac's law, you understand that increase in temperature is directly proportional to increment in your pressure, and the vice versa. If you reduce your pressure, your temperature reduces. So we are expected to carry out two opposite actions: compression, which raises our temperature, and then cooling, which drops the temperature. And based on research, you understand that we need to be at a temperature of around 6 to 8 bar, but we will be working with the high end 8 bar for our cryogenic distillation. We need to be at around 8 bar before we go inside the distillation column, and we need to be at a temperature of negative 160 between negative 160 to negative 185. Now that's a very, very low temperature and we need to compress at the moment we compress, we expect our temperature to go up, and that's why we have intercooling in between to drop that temperature because we need a very cold temperature, and at the same time we need increase in pressure. So that's why they go hand in hand. When you carry out compression, you immediately carry out intercooling control these to control these operations and conditions to fulfill your criteria for going inside the distillation column. And some of you might be wondering why we are carrying out three-stage compression, not just a single compression and intercooling. Now that's very, very much possible, but then the workload and heat load on a single compressor and a cooler would be much. So this is just more about spreading the heat load and workload across the equipment for safety and efficiency factors. So with this, we can go on ahead and start our compression. Remember, we're currently at 1 bar and we need to be at around 8 bar before we go inside our column. For the temperature at 25 Celsius, we need to be at, let's say, let's work with negative 180 for now and see if it gives us that vapor fraction that we desire 0.45 or less. Now, since we're at 1 bar and we need to get ourselves to 8 bar, we understand that we have a total change in pressure of 7 bar. 7 bar plus 1 bar gives us 8 bar. So split across three compressors, 7 bar, we could say we would be carrying out 2.5, 2.5, that's 5, and then the last compressor carries out a change in pressure of 2 bar. So plug in our airstream, label this as ecomp1. Just fix that up. Ecomp1 outlets compressed air 1. We specify our pressure. Change in pressure. It's an increment, remember. Let's just say this is about 2.5 bar. Good. As you can see, we're at 2.5 bar, and just look at the mag, mag, magnificent increment in temperature. Remember, we just raised the pressure from 1 bar to 3.5 bar, basically 2.5 for the change in pressure, and the temperature spiked up, basically going completely the opposite direction of where we need to be with respect to temperature. We need to be at around negative 185, 180, but then we're having positive 193. So that's much. We need to control that temperature through cooling. Now, this is just for the purpose of this design to make things easier and the content shorter. But then we're going to be using a cooler. Ordinarily, you are supposed to use a refrigeration circle, which we covered in our previous content, or a heat exchanger, which we also covered. So ordinarily, you use a heat exchanger, or most commonly a refrigeration circle, but we're just going to be using a cooler to just carry out the cooling. We're going to call this E cooler 1. The outlet, we're going to call this cold air 1. Then we're going to give it a change in, let's see, change in temperature, pressure, which should be specified. Now, another thing we need to take note of is that equipment such as columns, heat exchangers, coolers, heaters, we experience pressure drops inside these equipment, typically around 0.1 bar to 1 bar. So for this work, we're going to be assuming that we have a pressure drop of around 0.3 for each of those coolers. 0.3 pressure drop rather, that's 0.3. So 0.3 minus 3.5, that's 3.2 bar. All right, then take ourselves to a temperature of a very cool temperature of, let's say, negative 20. All right, and we are still in the vapor fraction of 1. With this, we have carried out our first stage of compression and intercooling. So we drop the second compressor. Alright, different compressor, cooled air, E comp 2. Now we call this compressed air 2, compressed air 2. And then we give it a change in pressure of 2 bar also, 2.5 bar rather. And that takes us to 5.7 bar, and we move from our negative 20 temperature of negative 20 back to 40.86 Celsius. So we need to cool this. So we carry our second stage into cooling. We plug this in, call this E cooler 2, call this cooled air 2. Let's just fix that up. Air 2, much better. And then we give a, remember, pressure drop 0.3. Why do I keep doing that? 5.4. And then we're going to be around a temperature of negative, let's say negative 120. And then good. Let's just take this out. This is much better. So second stage compression and intercooling successfully carried out, and then the third stage pressure, cooled air, E comp V, and then compressed air E. We're going to give this a change of pressure. We're currently at what temperature? Pressure 5.4, and we need to be at 8. So we increase the, let's say 2.9. Say 2.9. All right, 2.9 gets us to 8.3. And we are down to negative 92.5 Celsius. Gained heat due to the compression. And then move out, carry out cooling, in E cooler B, cool air B, pressure drop of 0.3 gives us 8 bar, and then let's situate ourselves at a temperature of negative 170 at 0.34 bar. Let's try and push it up to like 0.45 and see what that gives us. 0. Say 0. Negative 180 completely. Let's say 165. Alright, doesn't do. Negative 170, negative 169. Nope, negative 169, negative 169.4. Nope, negative 169.8. Alright, that's good. We are at a vapor fraction of 0.423, almost 0.4. Now, the reason for this vapor fraction is that it's more suitable for separation when we are at a vapor fraction of a mixed vapor fraction predominantly made up of liquid. So with this, we have carried out our three-stage compression and intercooling, and we are ready to go inside our distillation column to carry out our cryogenic distillation. So next up, we're plugging in our distillation column. Most complex equipment in Aspen HYSYS, but hopefully it goes well for us. For those of you who do not know how to operate the distillation column, we have a content based on that in our beginners. Guinness content, so you could check that out. Firstly, we start out by labeling our energy stream for the condenser, and we do the same for the boiler. And for our condenser, we're going to be using a full reflux because we're only expecting nitrogen and hydrogen, nitrogen at the top and oxygen rather at the bottom. So we're going to name this nitrogen. For the bottom, so we're going to call this oxygen. Plug in our inlet stream, which is cold air 3. We're going to go to the next slide. But take note that we're entering at the 5th stage of our distillation column. We're having 10 stages. Next up, we're going to be working with a regular reboiler, HYSYS reboiler 1 through setting, our reboiler configuration. Next, for our condenser pressure, we expect the reboiler pressure to be higher than the condenser pressure. Avoid the reverse flow. So we could just label this as 7.5. 7.5. We label this as 7. Remember, we're going into the distillation column at 8 bar. Let's specify a pressure drop of 0.5 bar, 0.5 bar. Pressure reversal detected. I think it's the other way around. 7.5 bar. Good, to avoid a reverse. And for the temperature, it's optional, so we're going to allow Aspen HYSYS to calculate that for us automatically. The flux ratio, I like to work with 1.5 first of all. And for the vapor rates, right? That's the flow rate we're expecting at the top. That's basically for nitrogen. You need to specify that. And we currently have a total of 1,000 kilogram mole per hour going inside the column. So let's start with 400, expecting 400 kilogram mole per hour of our nitrogen. All right, so we're done. Hopefully it converges when we click on run, which it does luckily. So that's one step. Now we need to take a look at our returns to see where exactly we are. For nitrogen, we're currently having 400 kilogram mole per hour like we specified as our vapor rates inside our distillation column. The mole fraction, we're having 97.85% of nitrogen currently present inside the stream, which that's a good fraction, a good percentage with respect to mole fraction. But remember that that is not our quantity in any way. Calculate our quantity as we have covered previously. We multiply the flow rates by the fractions. In our case, we are working with the mole fraction, so we multiply by the molar flow rates to compare. So we need to compare the two particular streams with respect to this nitrogen component. This is the inlet where we have our feed going inside the column, and then this is the product. So we need to compare the amount of nitrogen present inside our feed and the amount of nitrogen present in our nitrogen stream, basically the product stream representing nitrogen. To do that, we said we multiply the molar flow rate by our mole fractions, since we're working with the mole fractions, and we have 1,000 kilogram mole per hour here. And then we have 78.1% of nitrogen. So if you do multiply that, we get a quantity of 781 with respect to the nitrogen present inside our feed. That's the total nitrogen present in this air mixture, 781. To get that right, kilogram, yes, 781 kilogram. And then kilogram mole. And then for the mole fractions, we're having 97.85%. So we're going to multiply 97.85% by 400. So by doing that, 400 times 0.9785, we have 391.4. So that's basically around not even up to half of the total. Remember, the total nitrogen present in our feed was 781, and for the products in the product stream, the nitrogen present is 391.4. So we haven't even gotten half of our nitrogen in the stream above. So we need to make some alterations to our column to see how we can make that work. So what we might just do is we could just increase our vapor rates. Let's say we push it up to about 600 kilogram mole per hour, and then with that we just take this off, and then we inspect our nitrogen product stream. Currently having a flow rate, molar flow rate of 600, and currently having 98.01%. So we multiply 0.9801 times 600, and that's 588.6. So we previously had 191.4 when we were working with 400 kilogram mole per hour. We pushed that up to 600, and we're currently having for nitrogen 588.6. All right. So let's say we just tweak this and take it to 700. We're currently having 798.02. It barely changed. So 0.02 times 700. That's currently 686.14. So remember, we have a total of 781. So we're almost there. We just need to add this up. All right, 96. Currently having We're currently having 96.6%. So we put that in 0.9660 times 800. That's currently 772.8. We need to be around 781. That's our total. So let's see if we could just get ourselves there. Currently, let's have a check with respect to percentage to see how many percent of nitrogen we are able to recover in our stream. The input, remember, for the feed, the total nitrogen present in the feed is 781, and currently using 800 kilogram mole per hour as our vapor rate. So we're currently having a quantity of nitrogen in our product stream to be 772.8. So to get the percentage, we divide the quantity of nitrogen present in the product by the total nitrogen, and then we multiply by 100 per percentage. So to do that, we're just going to simply have 772.8 all over 781 times 100. And with that, we're currently having 98.95% nitrogen being recovered. Now that's much. That's way above what we need. We needed about we needed a value greater than 95% for recovery, and we're currently having 98.9, which is approximately 99% nitrogen being recovered. So I believe that's a good benchmark. So we're going to do the same thing for our bottoms for the oxygen to calculate how much we have. But the flow rate of the oxygen is currently 200 because we have 800 for the vapor rate, and the bottom we expect 200, a total of 1000, which that's our feed, basically obeying continuity equation. So we currently have 92.76% for our nitrogen here. So we're going to do 0.9276 times 200, and that's 185.2. Now that's what we have for our nitrogen product stream. That's what we currently have, 185.52. So we're going to need we need to check our oxygen, the the total oxygen present in our feed. That was for our product. This is for our feed. And for the oxygen, we have 20.9%. So 0.9, 0.2, 0.2090 times 200. And that's a value of, rather not 200, 1,000, because that's the total. 1,000, that gives us a total of 209. So 209, and we currently have 185.52. So we're going to convert this into percentage. Let's find the recovery rate in percentage as we did for nitrogen. It's simply the the amount of the amount of nitrogen present in the product stream divided by the amount of total oxygen. We're talking about oxygen right now. The amount of oxygen present in our product stream divided by the amount of oxygen present in our total feed. So it's going to basically be 185.52 divided by 209 multiplied by 100. And with that, we have 88.765%. Now, that's below the 95, greater than 95% benchmark that we have. So we're going to tweak this a little bit. Let's bring this back to 700. And by bringing the vapor rate back to 700, that's for our nitrogen, we expect this to become 300, which, okay, this is the feed. The feed doesn't change when we tweak the vapor rate. It's constant. Only the vapor rate only affects the product. So this is the product for oxygen. It's currently 299.8, approximately 300. So, and we currently have 65.61% for nitrogen. So we're going to do that again. 0.6561 times 300. Just work with the approximate value. The accurate value of 299.8, which is 196.69. So put that in percentage, we have a 196.69 over 209 times 100, and that gives us 94. So 94 isn't where we need to be. We need to be greater than 95. So let's make this 670. By making this 670, you expect this to be 330, which it is. So with that, we're currently on 59%, 59.79% oxygen, and we go 0.5979 times 330. That gives us 197.3. So 197.3 divided by 209 times 100 to represent that in percentage, and we have 94.4. So we need to go down. Let's make this 600. Let's see what 600 looks like. All right, 600 makes us have a 400 for our oxygen. Mind you, the more we reduce our vapor rates, the more the recovery rate of our nitrogen is affected. It's dropped basically, so we need to check the recovery rate of our nitrogen after we meet the benchmark of the oxygen. So it's more like an iteration process that we have to manually do. So we're currently having 400 for the flow rate of our oxygen, and we're currently at 49.59. So we go 0.4959 multiplied by 400, and that gives us 198.36. So 198.36 all over 209 multiplied by 100 gives us 94.9. Well, that's approximately 95%, but we need to be greater than 95%. So we need to drop this to 560. Let's see what 560 looks like. 560 gives us a 440, right? 440 and we're on 45.2%. So 0.4520 multiplied by 440 gives us 198, 198.8. Right. So 198.88 all over 209 multiplied by 100 gives us 95.15. And that's slightly greater than 95%. Let's try and make it go up to 95.5. By doing that, we could label this. Let's make this 540. Right. 540 makes us have 43.31% of oxygen with a flow rate of 460. Right. So 0.433.1 0.4331 times 540, if I'm right, rather 460 gives us 199.22. Now 199.226 over 209 multiplied by 100 gives us 95.32. Wow, we're still not there. Let's make this 530. Right, this makes us 470, yes, and 42.42. So for 0.4242 times 470 gives us 199.37. Now 199.374 over 100, not 100 rather, 209 times 100 gives us 95.39. Oh my days. You know what? Let's make this 500. So it's equally split. It's equally split across the top stream and bottom stream, basically nitrogen oxide stream. This gives us 39.93. So 0.3996 multiplied by 500 gives us 199.8. Now 199.8 over 209 multiplied by 100 gives us 95.59 finally. So that's greater than 95, slightly greater. Then we have to check for our nitrogen to see if it's still within our recovery spec, which I doubt that much, but let's check. So we go 0.978, 0.9794 multiplied by 500 gives us 489.7. Wow. Wow. we dropped. We significantly dropped. Oof. Let's check that in percentage. Let's see. 489.7 over 781 multiplied by 100 gives us 62.7. So this, I'm pretty much sure that we can now use a single column to achieve those specs. We might not really be able to use a single column to achieve those specs. But before we conclude, let's try checking out the specs like our rate, our molar flow rate. Let's see if it's possible. Use our molar flow rates get better yields because the boiling points between the nitrogen and oxygen, the oxygen has a higher boiling point, so most of the hydrogen boils off, but then it takes a little bit of the oxygen with it because they are not too far apart their boiling points. So it takes a little bit of the oxygen with it, and with that we cannot achieve that huge amount of separation and proper yield of 95% each. So with that, what I believe, if we're not able to use a single column, we might need to use a double column where we concentrate on getting the 95% for one of the streams, and then we concentrate on working on the other stream with the second column to achieve the yield of the 95% also. But we'll look at that shortly. So let's just put this back in order. Put this back in order. Around, put this back on 700 or 800 rather. It gives us yield of 90, it's around 99%. So let's look at the reflux ratio. Let's put this on 2 and see if our system converges, which it does. And this reflux rate overhead, right? Let's see what it looks like up here. 800 and 97.06. So we're going to go at 0.9706 multiplied by 800. That gives us 776.48. That's very close to 781. Let's put down percentage 776.48 over 781 multiplied by 100 gives us 99%. Right. Let's take a look at our oxygen. It's currently at 200 and 94.67%. So let's see what that looks like. Right, so 0.9467 multiplied by 200, 189.34, then 189.34 gives us 189.34 over 209 multiplied by 100 gives us 90.5. Now, we're having better results right now because we tweaked our reflux ratio from 1.5 to 2, and that's given us a better results. Basically, earlier we were having around 99, the ratio of 99 to 99 recovery for nitrogen, and then around 62 for our oxygen using 800 kilogram mole vapor rates. But now we're currently having 99 to 90.59. So let's see if we could just take this down to 900. Right, that's significantly dropped us. 800. Let's see, 750. 750. All right. So we're currently having 0.8. 0.8033 multiplied by 250, which is 200. That's very good. 200. Then so we're having 200.825 over 209. Multiplied by 100. That gives us 96.085. So that's above 95%. And for our nitrogen, let's see what it looks like having 750. Let's see if it's still within our spec. 0.9873 multiplied by 750 gives us 740. So 740.475 all over 781 multiplied by 100 gives us 94.81. And that's very, very, very close. Very close. Very close. So we might need to tweak this a little bit. Say around 780. See what 780 looks like. So we're going to have 0.9830 multiplied by 780, and that gives us 766.74 all over 766.74 all over 781 multiplied by a thousand or 100 rather. That gives us 98.174. So we are back in spec. So let's check that for oxygen. We're currently having 219.9, approximately 220, and currently having 89.96. So let's see if we're within spec. 0.8996 times 220, right? 197.9. So 197.9 all over 209. 209 multiplied by 100 gives us 94.6. Oh my please. Oh, wow. Basically a tug of war between the two of them. So let's try 760. See if that's the breaking point for us. Working with 760, we have a flow rate for oxygen to be 240. So, and we're currently having a 3.44% oxygen. So 0.8344 multiplied by 240 gives us 200.256 all over 209 multiplied by 100 gives us 95.81%. So let's check if our nitrogen, hopefully it works out. Hopefully it works out. Hopefully 760 and 98.6. So 0.9866 multiplied by 760 gives us 749. 749.816 all over 781 multiplied by 100 gives us 96. Finally, we are on spec. Currently having 79% recovery rate for our nitrogen and about 95.8% recovery for our oxygen. And with this, we have successfully separated our air mixture into nitrogen and oxygen, having carried out a 3-stage compression and intercooling and having a recovery rate of greater than 95%. Wow. Just at the right time, having a recovery rate of 96% for our nitrogen and 95.8% for our oxygen. This, we have successfully carried out our simulation. Mission accomplished. If you followed us down this far, as always, make sure to like, subscribe, click on the notification icon, and drop a comment if you found this video helpful. Thank you very much. See you soon.